Good morning. My name is Francisco Carrera, and I would like to start by thanking the organizers for inviting me to give this talk. I would also like to apologize to all of you for not being able to give this talk in person and having to resort to this less than ideal method. Anyway, my talk is about Athena, a European Space Agency flagship X-ray observatory to investigate the hot and energetic universe and many other things that you, the community, will propose when Athena flies. This is a team effort, a very large team. I would like to especially mention Silvia and Maite from the Athena Community Office, the rest of the colleagues from the office, the Athena Science Study team, and the huge Athena community, whom we warmly thank for their work on Athena during the years. I will start by presenting Athena in a nutshell. Then I will elaborate about the mission concept, its optics and instruments. Afterwards, I will develop a bit more the Athena science themes, skimming over some of them because there are going to be many talks after mine, hopefully in person and more entertaining. I will then emphasize the role of Athena in the context of multi-messenger landscape that will be there when it is launched. I will finish by highlighting the capabilities of the observatory compared to other existing or in progress. I will leave some minutes for Matteo Guainazzi, the Athena study scientist and the leader of the Athena efforts for quite some years now, to explain the latest developments about the project status. Athena is the second launch mission of the ESA Cosmic Vision program. It was proposed to address the science theme, the hot and energetic universe, which articulates in two pressing questions. The first one is how does baryonic matter evolve into the large-scale structure present in the universe today? And the second one is how do black holes evolve and, in so doing, influence the universe? This will be answered through a next-generation X-ray observatory, not an experiment, which will also tackle any other open astronomical mysteries at the time it flies. You can get more information in the Athena community webpage. Okay, so with a bit more detail, the Athena Observatory has a single telescope using silicon pole optics with a focal length of 12 meters and two instruments, WFI, which is designed for sensitive imaging and timing, and the X-IFU, which is designed for spatially-resolved high-resolution spectroscopy, both with high count rate capabilities, as we will see in a few minutes. The idea is that the telescope, the mirror assembly will move and will direct the light between the two instruments. The idea is the Athena should be launched in the early 2030s with an Ariane 6.4 to an L1 halo orbit. And the lifetime nominal is going to be 4 years, but it may have some extensions. I would like to remind you that the XMM was supposed to be for 2 years originally, and now it's going for more than 20 and hopefully for many more, as its colleague Chandra, which together have made a lot of progress in X-ray astronomy and in all branches of astronomy. The Athena optics follow a new concept of lightweight silicon pores, each one of them replicating a Volter-Schwarzschild type 1 geometry. These pores are grouped into mirror modules, as you can see here to my left, and then these modules are grouped into an annular geometry forming the mirror. The expected performance is a half energy width of 5 arc seconds on axis. At the moment, 8 arc seconds is half energy width is demonstrated. The latest mirrors have 6.5 arc seconds, and there is a vigorous technical development going on that may allow us to reach close to the expected value. Whatever the central half energy width then turns out to be, there is a graceful degradation of axis, so it doesn't grow very much with of axis because it's optimized for large field of view. And the effective area is 1.4 square meters at 1 kV and 0.25 square meters at 6 kV, although there is a slight shortfall on this last number. The WFI is a silicon active pixel detector based on depth first. You can see here the performances of the detector. It has typical spectral resolutions of silicon, as you can see in this sample over here. The pixel size over samples of the PSF. The field of view is pretty nice, 40 by 30 square minutes, a bit larger than XMM. You can see up here an example of a simulation on one of the famous deep fields. There is a separate chip for fast readout for the brighter sources, and the readout of the normal chip, of the large area chip, are good enough to avoid a pile-up to fairly high brightnesses. The consortium is led by MPE with participation from other European countries. You can find the list over here, and also NASA. This detector is optimized for sensitive wide field imaging and intermediate resolution spectroscopy up to very bright sources. The X-ray integral field unit, X-IFU, is a cryogenic imaging spectrometer based on transition X sensors operating very close to 0 Kelvin, which also have a background radiation subsystem which is cryogenic as well. You can see the performance parameters here. So the energy resolution is 2.5 eV, very nice, as you can appreciate in this spectrum over here. The diameter is 5 arc minutes, and the pixel size is smaller than 5 arc seconds. It's led by a consortium led by IRAP CNES in France, with Netherlands and Italy providing important contributions, and other European countries as well, as you can see down here. There are also contributions from Japan and the United States. This instrument is providing both spatially resolved high spectral resolution and also high count rate capability, enhanced by the possibility of defocus the mirror, which can also benefit the WFI. As already said, the Athena X-ray Observatory was proposed to answer the hot energetic universe science theme. Essentially, the hot universe is to understand the location and physical characteristics of more than half the ordinary matter in the present-day universe, and the energetic universe is to do with the growth of supermassive black holes and how do they influence or not their host galaxies. On top of that, 15% of the energy output of the universe is done in X-rays. Okay, so the hot universe, we see there on the right-hand side a simulated image of a part of the sky with WFI, and you see that there are point-like sources, which are supermassive black holes, accreting supermassive black holes, but you can also see some diffuse sources. All this is hot gas in the centers of groups and clusters. And what we can see on the left is a cosmological simulation showing the distribution of gas of different temperatures, and you can see that in the nodes of the cosmic web there is very hot gas, which encompasses most of the baryonic material at the moment. Athena will detect groups and clusters of galaxies up to fairly high redshift, and it will also study in very much detail the clusters of galaxies. I'm not going to dwell much on this because there is another talk by Esra Bulbul, and she will cover this in much more detail than I will be able to. Clusters of galaxies are interesting not only because of their own physical properties or because of what they tell us about cosmology, but also because they are closed boxes, which means that the gas contained in them is a summary of the history of the chemical enrichment of the universe. As you can see in this plot over here, this is a simulated X-IFU spectrum of cluster gas. There are very well-defined features of different elements which can be used to compile this plot over here, in which for each element the different contribution from different origins can be studied and constrained. The gas in clusters of galaxies shows bulk motion and turbulence, which Athena will be able to measure down to 20 kilometers per second. As you can see in this plot over here, this compares what Athena will see with an equivalent length observation by Hitomi. And with the X-IFU, you not only get the spectral resolution, but you can also have spectrally resolved plots. This is another simulation showing the bulk motion and turbulence in gas in a cluster of galaxies of redshift 0.1. We're going to hear a lot about AGN in these couple of days, but it's important that when an AGN is in a cluster, the influence of the AGN can extend over the whole intercluster medium, and that's nice because, for example, in this simulation we can see here there are ripples well beyond the AGN host galaxy, which is tiny thing over here. This is for the Perseus cluster nearby, and this is for a cluster at 0.05. And these ripples give us the history of the AGN fueling and the gas cooling in the cluster. About half of the baryons in present-day universe are in a warm, hot intergalactic medium at temperatures between 10 to the 5 and 10 to the 7, as shown by simulations, as the ones to be discussed by Tony to a minute. This material is in unrealized and filamentary distribution, which is starting to be detected now, as doubtless Angie Veronica will tell us in her talk. In addition to detecting this material in emission directly, it can also be detected in absorption, as shown in this scheme here. We have a bright background source going through the cosmic web, and we detect the imprint of this material on the spectrum of the background source. This has already been done by Nicastro and collaborators using RGS, almost 2 megaseconds of RGS, and there are the imprints of the material over here. This was, as I said, 2 megaseconds. In 150 kiloseconds with X-IFU, this is a simulation of the same data, we could detect it with much more detail. In addition, the highest effective area will allow us to also do this with many other sidelines and have a better understanding of the distribution of this material in the universe. And we go into the energetic universe, black holes. Again, I'm not going to dwell on this. Athena has planned to have a large survey that covers a large area of the sky. It will detect many sources at low and high redshift. As I said, I will let the experts talk: Giorgio Lanfisi, Johannes Buchner, Melanie Habussi, Julian Wolf, Matteo Angelinelli, Ivan Muñoz Rodriguez, Andrea Cesas, and Carlota Gruppioni. The last two are going to talk more about perhaps galaxies than AGN, and also let's see the very exciting possibility of using X-ray AGN as cosmological probes with originality. There are also talks about the obscure section of this AGN by Rivail Lalux and Mislav Balokovic, so I will let you with in their capable hands. Of course, AGN are not only interesting because of the population studies and what they tell us about the assembly of galaxies, but they're also interesting in their own right. And with Athena, we'll be able to study their structure, the jet and disk relation, and also the supermassive black hole spins. Spins are very interesting because measuring them and the populations will tell us about how the supermassive black holes were assembled. This is going to be the topic of Peter Burman and Alessandro Trinca's talks. AGN can influence their host galaxies through AGN winds and outflows, and X-rays are particularly interesting to study this because these flows are originated very close to the black hole where X-rays come from. For example, we can see in this simulation here on the left, we can see the imprints of outflowing hot gas at speeds close to the speed of light, called UFOs or ultra-fast outflows. The WFI is going to be able to detect this in a large population again in the survey, and then with X-IFU we can measure with detail their energetics, which will tell us whether or how much are they able to actually influence the galaxy. These AGN outflows and also supernova outflows will move gas, will enrich the circumgalactic medium. This is the topic of Annalisa Pilepic's talk. Moving a bit away from supermassive black holes, Athena will also contribute to the study of luminous extragalactic transients in the time domain universe, which is now blooming very rapidly. In particular, it has a fast target opportunity capabilities with able to react in 4 hours and observe 40% of the GRB afterglows for at least 50 kiloseconds. We have here one example of that. Another type of transient sources is that tidal disruption events, which Athena will also be able to study and reveal the composition of the flowing material and perhaps find if there are binary supermassive black holes and the presence of a supermassive black hole. Natalie Webb's talk is about the transient universe with XMM Newton, and hope a bit with Athena as well. and Shen Chaos is going to talk about the tidal disruption events. Okay, so the Athena was designed to address the hot and energetic universe, but of course Athena is an observatory that is expected to have a lot of influence in many other areas. So you can see here some examples. I'm not going to mention them all. You can see here an example of a X-IFU spectrum of Jupiter, and there's an X-IFU spectrum of a supernova remnant. In 2/3 of the Athena operational time life will be on open time for you, the community, to decide what to observe. So there will be many other discoveries to be made with Athena. And some of these discoveries will be in the topics covered by Antara Basu 6 and Julia Margalida 6 range. By the time flies in the early 2030s, Athena is not going to be alone in space. There are going to be many other observatories in space and on the ground, as you can see simplified over there. This is shown over here, in which we have redshifted to redshift 7 the spectrum of NGC 6240, which is an obscure source with a double aging nucleus and strong star formation. These coral lines here correspond to different plant or in work instrument, and you can see that all of them together will be able to constrain the spectrum of such a source if it exists. This is an example of they working together and doing things that none of them can do by themselves. The Athena team has developed a number of synergy studies with different observatories, with ESO. This is being published in this reference here. SK8 has been published in this reference here, and it's also been covered by Sophie Igo and Andre Messenger's talks. We have finished recently a third synergy exercise with multi-messenger observatories, which has been published in this reference you can see here, and will be soon published in a refereed paper. And we have started a synergy with the WHIM observatory in the time domain universe. So all these things I've shown you, all these studies, all these numbers I can show, all these nice spectra have just skimmed through, wouldn't have been able without the huge effort of the Athena Science Study team, which is these people here. You may not be able to read them, so I will tell them aloud. Matteo Guainazzi, Didier Varret, Paul Nandra, Massimo Capi, Judith Croston, Anne de Courchel, Jan-Willem de Herde, Luigi Piro, Nanda Rea, Thomas Reibrich, Norbert Werner, Randall Smith, and Hironori Matsumoto, from the last two from NASA and JAXA. This in turn rests on a huge Athena community, which I will not have time to say, but it's organized in the hot universe, the energetic universe, observatory science, telescope, and then mission performance here. So a huge thanks to all of them. This community is more than 1,000 people. So in order to help the Athena Science Study team to handle them, the Athena Community Office has been established, of which I have the honor to be the director, and it's led by the Instituto de Física Cantabria in Spain, together with Silvia, Maite, and other colleagues from IRAP, MP, and the University of Geneva. And what we do is to help in the organizational and scientific aspects of optimizing the community efforts, to keep the Athena community informed, and to develop communication and outreach activities around Athena. So yes, I'm just finishing. So let's finish with a couple of important points. Athena is a transformational observatory. We can see on the left-hand side here, this is the weak line sensitivity compared to WHIM, which is going to be a huge advanced WHIM, and Athena, a few years later, is going to be another huge advance, another factor of 10. The equivalent plots for RGS would be somewhere down here, another factor of 10. So it's going to be a huge improvement in high resolution spectroscopy, and it's also going to be a huge improvement on the capability of detecting faint sources. This is with respect to Chandra and XMM. Of course, the angular resolution is worse than on axis for Chandra, but that means that the confusion will not allow us to go as deep. But for reasonably pretty deep sources, even, you know, we're talking about 3 times 10 to the minus 17, or even 3 times 10 to the minus 17, we will be able to detect and characterize much better sources than any previous mission. Going into just brute large effective area, we are going to improve with high spectral resolution and spatial resolution anything before us, for example the XMM RGS, a factor of 70, and we are going to improve by a factor of 10 the EPIC PN and Chandra. Right, outlook. So Athena will be a transformational X-ray observatory. It's been designed to address the hot and energetic universe science theme, and it's expected to impact virtually every corner of astronomy and discover many things, many of which we cannot see now. It will be an essential part of the observational landscape in the early 2030s, together with ALMA, ELT, SKA, CTA, LISA, and other observatories present at the time. And there is a vibrant, huge community supporting it. So you can follow the Athena advances in the web, in Twitter and Facebook, and the email that you can see there. That's the ACO email. And I leave now Matteo to tell you about the Athena status and prospects. Thank you very much.